Okay. There were again some very good questions in the break, including pointing out a typo here. This should have been a multiplication, not a summation. Thank you. Okay, so we were here discussing the location estimator, nothing to do with PCA yet. But location estimator simply means we have samples. We have samples, and we want to estimate their location. And this likelihood, in the maximum likelihood estimator, we assume that we know the probability distribution which our samples follow, which could be normal or Laplace or Cauchy. And then under this assumption, we try and find the best possible parameter. I made a bump here, I'm sorry. Good. Okay, and now if you think about what the standard estimator for the mean that you all know what it does is, okay, for the normal, we would put in here the Gaussian. Yeah, we would put in e to the minus 1/2 x minus mu squared. Or if we take the negative log likelihood, then we take this sum over parabolae. Yeah, so for, let's say, for the normal distribution or L2, what we do is that we really implicitly, we have a parabola here, and a parabola there, and a parabola there. One located at every sample, and we sum all of them up. And you know that the sum of parabola is a parabola, and it will have its center, well, somewhere to the right, yeah? Because this one here, okay, so if I sum all of them up, I obtain something which maybe looks like so. That's a parabola. Probably I've exaggerated a little bit, but the mean is not really close to where the other observations are, but it has been affected by this outlier. I have exaggerated a little. Yeah? I think it should be more to the left. And by the way, you can think about, what is the height of this parabola? It tells you something about, the closer the observations are together, the lower or the less far away this the bottom of this parabola will be from 0. And the more points are spread about, the higher it will be. And this has a clear interpretation in statistics, this height. You can think about that. Okay, so this was for L2. Let's do L1. I'm trying to copy the same observations. This time we have potentials or loss functions which look like so. Again, we sum all of them up. And we get something interesting. So in this case, I have 1, 2, 3, 4, 5, 6 points. So I know that to the left of this point, the slope will be -6 because I am adding up all of these functions. And at this point, one of them change. So let's look at the slope. Slope here to the left of this point is going to be -6. Here, well, we lose one of the contributions of negative slope, and we get one contribution to the positive slope, so it's going to change to -4, and here to -2, and here it's 0, +2, +4, and then +6. And the interesting thing here is that for this even number of points, the slope is 0 in between here. Yeah? So that means the median, which is associated with the L1 loss, for an odd number of samples, it's well defined. It's your sample in the middle. But for an even number of samples, you have some degeneracy here. And now I'm going to have difficulty, drawing this nicely, but basically, okay, I'm rescaling by some arbitrary parameter, and I have something which becomes a little bit flatter at each of these observations, and then it becomes a little bit steeper. Okay, exaggerated a little bit, but you get the idea. Yeah? So here we had this yellow overall sum, here we have this green overall sum, and the median now lies in this interval. And you see that this is a robust estimator. In particular, the minimum of this set of function will not change as I move about this outlier. If this outlier goes to infinity, the location of this kink will change, but the minimum will not change. The minimum will only change if my outlier walks to the other side of my current minimum. And that's what we saw here. Yeah? So it doesn't matter how far the outlier is. All right, that was for the L1 median. And now let's do Tukey. And I will again try and copy the data. All right, and for Tukey, we now have these funny potentials that are located on my samples. And I have this important bandwidth parameter. All right, and we go on and we go on. And this is going to look messy. Okay, so these are the functions, and now I can add them up, and I will obtain something that looks broadly like so. Yeah, so the sum of all of these is going to be that. And now we see something interesting, namely here, okay, it was sensitive to outliers, but we had a unique optimum. Here, this was much less sensitive to outliers. We had an optimum which was almost unique, yeah, up to this degeneracy here. Here, suddenly, we start seeing local minima. So on the one hand, it is super robust to outliers, but on the other hand, it becomes difficult to search for this minimum. Now, in one dimension, not a problem. We can sample systematically and see where is the lowest minimum. But think higher dimensions, and it starts to become a non-trivial problem. Okay, and now we can come back to robust PCA and start thinking about how we could achieve it. Yes? Oh, this is now, I think, just what I have wiped. So in these maximum likelihood estimators, we always assume that the data follows a parametric distribution, and we just look for the parameters of the distribution. Yeah, and here, if we use this one, we implicitly express the belief that the data is normally distributed around some true parameter mu0, which we don't know and which we're trying to estimate. Here we implicitly believe the data is Laplace distributed. This one does not have any distribution associated with it. Yeah? So in practical terms, people, in particular machine learning, they don't really think that their data is normally distributed. Yeah? So when you train a neural network, do something complicated, and let's say you use the L2 loss at the end, people don't really believe that it's normally distributed. They just use it because whatever, it converges nicely or something. And then there is some empiricism of what loss function do you want to use. And then the argument goes more about these loss functions. And then robust statisticians, they say, I don't care if a distribution doesn't exist. My data comes from the real world. It comes with outliers. There is no simple parametric distribution that describes what's going on, but I still want the best possible location estimator. And so I do Tukey. Okay. More questions? All right, then now let's invent robust PCA. I'm drawing my usual picture. I say the data has been mean-centered. And so we consider trial solutions that go through the origin. We have some mean outlier or outliers. And so we're looking for a function that goes through the origin. This is my set of functions or of candidates that I'm considering. And now for any single candidate, we can say that I'm initializing with some function, for example, this one here. And then we have we can project each point onto it. And then we can ask for the loss associated with this residual. And so far, we were looking at square distances, and I was drawing a spring to say, physically that's what it would be. Now, Tukey would be something like we have a string here. I cannot say that it snaps. I cannot say that it breaks because it still contributes to the loss here. But I could invent some function. Why not? I could invent some function that goes up, and then beyond some bandwidth, I could just say my spring breaks, and it doesn't even contribute at all. For example, people don't really use this, but this would also be very robust. Okay, so now we replace our harmonic spring with something else. And now I have, but we already saw here that we had this problem of local minima. So now if we agree on, let's use Tukey, for example. Let's do Tukey PCA. Then there will be this question of local minima. And now I could parameterize in this picture here. Yeah? I could parameterize the appearance of my function with a single parameter. Let's say I could take this angle phi or something, and I could ask for the loss that we see as a function of phi. And if we use Tukey and if we have some outlier here, I'm pretty sure that as I plot phi here, I will get a very deep minimum near the good region if I choose my bandwidth appropriately. But I would also get somewhere a blip where I fit this point better. And then the whole thing has periodic boundary conditions. Okay, so in one dimension, fine, you know, we can just sample it and say that, all right, this minimum is much deeper than that one. But now think about higher dimensions. Yeah? So we have this point cloud in a high dimensional space. We might have outliers. We look for the first principal component. And so my question to you is, what could be done to initialize this? How could we find this first principal component in a high dimensional space? And in particular, you can think about methods which are randomized. Yeah? So let's say you can use just a subset of the points to estimate something. Maybe you can, yeah. You know, you have a lot of creative freedom. So, you know, please find a neighbor and, you know, take 5 minutes to think about this question of how would you initialize, or how could we come to a good estimator if this is high dimensional, and if we want to use a kind of Tukey loss to measure our violation here. Up to you to invent robust PCA. So let's see what you have found. How can we initialize, or how can we find a good local optimum? Yes? Oh, well, okay, you've spoken before. Let's have somebody else. Yeah?
Simulate annealing. Several times and check for the lowest result.
Okay, so the suggestion was simulate annealing. So we would start with, we would have a temperature parameter, and we would be willing to, in a Monte Carlo sense, we would be willing to take bad steps in the sense of loss with some probability. And then we could have temperature schedules and so on. And actually, simulated annealing is, if we have infinite compute, is guaranteed to find the global optimum. But it takes a long time. But a valid suggestion. Do you have other suggestions? Yes?
We have more between how we could orient the function we want to do. If we take the degree of freedom and put them like this is one-dimensional potential, we now do dimensional potential, we could find the optimum of this potential, but it might also give potential to have 10, 20 dimensions.
Yes. So here the parameter was a just one angle in. If you use one more dimension and we're still looking for the first principal component, we would talk about the surface of a sphere and then talk about surface of a hypersphere and so on. So doing that exhaustively becomes prohibitive. You're right. So yes. Gradient descent. So gradient descent is good to let us fall into the closest local optimum. So like if we initialize with a yellow solution and we use Tukey with an appropriate bandwidth, gradient descent will help us fall here. Yes. But how do we find the good starting point?
This minimum, delete them, and find next minimum, or look if we can find a new minimum, and then we just check for all the minima, make the lowest one. It's like a little less effective than just simulating all over again.
Okay. So the suggestion was, let's start somehow. Let's do gradient descent. Let's delete all the points that, so for example, we start here, but we still haven't said how we start here. But we do gradient descent, then we delete all points that agree well. And then on the remaining points, the question is then what on the remaining points? Because the thing with Tukey is that it gives us very little gradient. Yeah. If we are far away from the solution, it gives us 0 gradient. But it's a good suggestion.
Maybe do some sort of adaptive gradient descent where the gradient, the length of the gradient changes depending on where you are in the local or control. I mean, if you start in the right-hand corner of the plot, for example, and we, by bad luck, we have the outlier minimum, you could say after so many rotations around the minimum, you just change the length to get out of it.
So the suggestion is to try and escape local minima by occasionally choosing a wild step length. But it's not clear that this wild step length in high dimensional space will, if we just walk in any direction, it's not so likely that we will find a deep minimum. So we need more suggestions. Yes? Uh-huh. Okay. So suggestion is to, I'm always repeating so that people on the video can hear something. So you say initialize with L1, which is has a unique optimum, and then track the minimum as we change the loss function. That's an interesting suggestion. Yes? Yeah?
the outlier. So the secondary minima are flat more than the global minima. And so you can make this 1, 2 more-code. And so you have always the global minima, but not always the secondary minima. So you can determine the global minima.
Very good. Yeah. So the suggestion was, let's start with a random subset of points, and this is a great suggestion, and this is in the literature. This is called RANSAC. Who has come across this before? Computer vision, yes? Exactly. What it means doesn't matter. It's called random sample consensus. But the idea here is to start with a small set of points. So pick a random subset. And in our case, so this random subset of points, we can decide how large should it be, but whenever we try and estimate, if we just want to estimate the first principal component, then it would really be enough if we actually, if we say that it goes through the, here in 2 dimensions, and if we insist that that the principal component goes through the origin, then just a single point is enough. Yeah, we sample a single point, and maybe we have sampled this one here, and then we say, okay, we initialize our principal component like so, by going through this point. And if we have now some fraction of inliers and some fraction of outliers, we can calculate, and that's a nice exercise. So if we have some let's say a fraction of inliers and some fraction of outliers, which together gives 1. We can, for example, pick a random subset of m points. And then, using high school math, you will be able to compute the probability that you have a subset free from outliers. Yeah, it depends only on this parameter or this fraction of inliers to outliers. And then you can say, all right, let's fit our model to the subset. And then do gradient descent or something like that to find a local optimum. And then you can repeat. And now the question is, well, how often should you repeat? So we have 2 parameters, yeah? All right, so for Tukey we have the bandwidth, okay? But beyond the bandwidth, we have to decide what is this fraction, how big is the subset of points that we're choosing, and how often do we repeat? And if I have some estimate of how many outliers do I expect, I can even calculate, again using high school math, how many experiments do I need to do, how often do I need to repeat, so that I will have at least 1 pure subset. And that's a very nice procedure to find good initializers in such kind of problems. Great. So, this is still state of the art, and it took people a few decades to find it, and you have found it in a few minutes. I'm proud of you. So, there were many, sorts of fragments, yeah, that things you said that went into this, and yeah, great result. Good. So this is how we can initialize a robust PCA estimator. And there's one thing I should still say, which is qualitatively different with these different loss functions that we've seen. I mentioned last time this notion of convexity. And let's again look at our three functions. So there are various definitions of convexity. But one definition asks, can I pick any point and any other point, and will I always lie above the function? So let's say this is x1 and this is x2. So I can ask, and then I can interpolate parametrically with, let's call it t, which goes from 0 to 1. And then I can ask, so for any points x1 and x2, and for t here in the interval from 0 and 1, is the following true? So if I evaluate my function at, let's see, what's the intermediate coordinate? It is, for example, t times x2 plus 1. Okay, now I got it the wrong way around. Let's say x1 here and x2 there. Okay, now it goes from right to left. But so we interpolate between the coordinates and we look at this function. And on the other hand, I can look at my function where I say, let's take t times f of x1 plus 1 minus t times f of x2. So this is the function evaluated at the various points, and this is the linear interpolation. And if the linear interpolation is always bigger than the function, then this thing is called convex. And if a strictly greater holds, then it's strictly convex. Yeah, so here, pick any point, and yes, our linear interpolation is above. Here, pick this point and pick that point. Yes, our interpolation is above, but pick this point and pick that point. And here I have entered the hell of non-convexity. And on Tuesday, I had this plot of, let's talk about optimization problems. And I said, this is the sea of non-convex optimization problems. And in there is this small island of happiness of convex optimization problems. And when talking about optimization theory, like 30 years back, the difference was always, do you do linear or nonlinear optimization? But the more crucial distinction is, do you have a convex or a non-convex optimization problem? And well, convex means that we can always find the minimum, and their convex means that the global minimum, the unique minimum, or the one minimum, it can be degenerate. Yeah, it can have some finite extent, like we've seen here, but there's always just one minimum, even if it can be degenerate. And so is it convex? Yes. Is it convex? Yes. Is it convex? No. And now if we add convex functions, this preserves the property of convexity. So in other words, here, if we sum up all these nice convex L2 losses, we end up with a convex sum. If we add up the nice convex L1 losses, we get something which I plotted down here, which is also still convex. If we add up these ugly non-convex functions, well, we end up with something which is non-convex. And the L1 loss is very special in the sense that it sits right at this limit here. Yeah, it's a convex optimization problem, so it's standing on the shore of this island of happiness, but one step further, and you're in the hell of non-convexity, or where sharks swim and so on. So because this function here is convex, but if it were bending back any so little bit, yeah, it would no longer be convex. All right, and this is why L1 is very popular, is a very popular choice. We will see it again when talking about regression problems and regularized regression, that this is a fantastic choice. Okay. And yeah, here I think, it's been a beauty. You've seen that it doesn't matter how far the outlier is. It doesn't change the location of the optimum. It only matters if the outlier lies to the right or to the left, but not where. And we can still find the solution efficiently. Not as easily, not in closed form as with the L2 loss, but still in a computationally efficient manner. All right. Good. And for the remaining time, I would like to start talking about nonlinear dimension reduction. So PCA is great. So why bother about nonlinear dimension reduction? And I'm here showing you the hello world of machine learning, which is a data set called MNIST. And MNIST are pictures of characters, of digits. So we have 10 classes, and MNIST are these 28 by 28 pictures. So that means we have, is it something like that? 784 something dimensions. Okay. 700 and some dimensions. And now, we like to think of pictures as pictures, but in machine learning, most of the time we deal with vectors. Yeah, so we can say, all right, we turn such a picture into a vector by just, reading out the values from left to right on the first line, and then continuing left to right on the second line, and then on the third line, and so on. Right, and then we get, so what is 28 squared? Is it 784? Is it? Yes, thank you. So we get a vector with this many dimensions, and we can say each digit, we consider it just as a vector with 784 dimensions. And then we can feed it into neural networks and do all kinds of things. No need to photograph this. I will give you the link to this document later. And then we could, for example, do PCA on this 784 dimensional space. And then, because these are digits, they have natural labels, yeah? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we can color the coordinates that we find according to those labels. Yeah, so here, the 784 dimensions were used to embed the points in 2 dimensions. And the label was used after the fact. It was not used in the PCA computation, but it was used after the fact to color according to the classes. So I didn't plot the legend, but I don't know, maybe yellow is 1 and red is 2 and whatever. Okay, so this is what PCA gives you. And, it's as always is a good starting point. So in particular, if, for example, you had some images in there which were completely black or completely white, you would see those as as outliers or cluster of outliers. So, PCA, it's always the good starting point. And then look here. This is a nonlinear method called UMAP, and it produces this kind of plot. And again, the labels were not used in finding the coordinates. Only the 784 numbers were used to find coordinates, to arrange the points somehow, and then the label was used to color them. And you see that the result is amazing. Yeah, it's not perfect, so some points are in the wrong cluster, but still superb. Yeah, and yeah, the same thing, you know, can be useful in physics. So here, for example, the gentleman on the right-hand side, Scott, used this in analyzing data in some detector, and then found that there were some funny things in the data, and these turned out to be above anode gas events. Yeah, so UMAP or TISNI is a very useful second step after doing PCA to look at your data. And I want to tell you briefly and in words how it works. Namely, you find nearest neighbors for, in the original high dimensional space, you find mutual nearest neighbors. Mutual nearest neighbor, the distinction is important because if we have here 3 points, so let's say we have points A, B, and C, then, and C is a bit further out, then B is a nearest neighbor for C, but C is not a nearest neighbor for A. Yeah? So you find the symmetric nearest neighbors using not the one nearest neighbor search, but you know, something like maybe the 10 nearest neighbors. That gives you a graph. Yeah? So each point has an edge to its 10 symmetric nearest neighbors. And then you do the following. You then say that, okay, I am looking for an embedding such that any points which are symmetric nearest neighbors, they experience this kind of potential. They want to be together, but if they're not together, it's not catastrophic. Yeah? It's a robust potential. And vice versa, any points which are not mutual nearest neighbors, they experience some repulsion. And then depending on what repulsive potential you use, maybe it might look like so, you end up with different embeddings such as UMAP, and basically the biggest two players in the field are UMAP and TISNI, and they produce very different looking pictures. And I want to show you a beautiful animation from Dimitri Kobak, who is one of the world, I think he's one of the absolute leading experts worldwide on these embedding methods. This was a bit fast. Let me try and show it again. So first make it big, and then how do I, okay. The points were randomly initialized. This is not MNIST, but some other data sets. The points were randomly initialized, and then they experienced these forces that I've just described. And then you see that you know, to really converge, it takes quite a bit of time. If you have 1 million points, you know, that's 1 million points interacting. That can take some time to compute, but it does give you amazing embeddings in the end. Yeah, and this is called neighbor embeddings. And again, thanks to Dimitri Kobak for this beautiful animation. And by the way, Dimitri was here last year to replace myself when for lectures here. We are very happy to have had him here. Okay. The potential, that was the TISNI potential. And that's really the one that I'm showing here, except that TISNI has, it's not drawn to scale. The repulsion is much stronger than what I've shown here.